Dear people, how are you? This is Dr. Venkat, and in the next few minutes, I would like to discuss with you on thermal expansion. Now, even before we go into today's session, I have three questions for you. The first one is, how many of us would like to get on a train and want to reach our destination safely without the train derailing? Huh? Raise your hands. How many of you? Excellent, excellent. Yeah, thank you. And the second question is, how many of us would like to get on a bridge knowing that we are going to reach the other end safely without the bridge collapsing? Huh? Yes, excellent. And the third question is, how many of us, as future engineers and future scholars, would like to design and manufacture products and systems that are resilient and sustainable? Nice. If you have risen your hands to all these three questions, we are going to have a very interesting and very useful few minutes discussing thermal expansion. Welcome to my lecture. In this particular session, I'm going to introduce you to thermal expansion and activate your interest in this engineering concept. And then we'll use mathematics as a tool to solve one of the thermal expansion problem. And I will introduce you to the associated mini project, which is very interdisciplinary and open-ended for you all to work with your peers. This would reinforce your learning. All about the train. Shall we go? Choo choo! My dear people, a couple of years ago, when I went to Paris, I went to Eiffel Tower. It was a freezing December day, and I met the engineer over there. And I asked him, "What is the height of the Eiffel Tower?" He said it is 330 meters. I was, wow, that is quite tall. And then a few months later, in August, on a hot day, I visited Eiffel Tower again and I met the same engineer. What a coincidence. And I asked him, "Oh, can you please remind me what is the height of Eiffel Tower?" He said it is 330.17 meter. I was quite surprised. My dear people, how is it possible for the Eiffel Tower to have grown by 17 centimeters in a span of few months? What do you think? Yeah, what do you say? What? Exactly, thermal expansion. Nice, nice. So, what is thermal expansion then? But whenever you heat a material, what happens is that it expands in its length. That is all thermal expansion is all about. Let us say we have a bar of steel of initial length L. Yeah, so it could be 2 meters, it could be 1 meter, it could be 10 centimeter. We just call it L. So the initial length of the bar is L, and then when I heat it up, all that happens is it expands a little bit, and this change in length is what we call as delta L. The triangle that you see here is the Greek symbol delta. Yeah, delta L is nothing but the change in length. Now you might ask me, Venkat, what if I freeze the material? Very good question. What do you think is going to happen? Huh? Tell me, do you think that as future physicists, engineers, and scholars, it is important for us to identify and measure thermal expansion? What do you say? What? Yes? Okay. Just because you said it is important, I'll show you how to do it. My dear people, to measure thermal expansion, it is very simple. Yeah, let me introduce you to the equation. Change in length delta L depends on three various factors. What are they? The first one is the material itself. Okay, now let me ask you. I take a 1 meter bar of copper, 1 meter bar of steel, bronze, brass, and then I heat them all to the same temperature. Do you think that they will all expand to the same length? What? No, exactly. Because different material have different property. And that property that makes different material to expand to different length is called as the coefficient of thermal expansion, or simply called as the thermal coefficient, and it is represented by the symbol alpha. The next factor is the initial length of the material. So, this is quite simple to conceptualize. Think of it. The longer the material, the more expansion. The smaller the material, less expansion. Yeah. And the third determinant, the final determinant of expansion, is the change in temperature. The more we heat the material, the more it expands. The less we heat the material, the less it expands. So, where T2 is the final temperature and T1 is the initial temperature. Yeah. So, the thermal expansion depends on the thermal coefficient, the initial length of the material, and the change in temperature. Now, if we combine all these things together to form an equation, there you go. That's all. Change in length delta L equals alpha times initial length times the change in temperature, and the unit is meter. I told you that it is very simple, didn't I? Huh? My dear people, if you want, why don't you just pause the video, rewatch the last few minutes so that it's easy for you? What do you say? Hmm? Whatever we have discussed until now is the linear expansion, in which the expansion happens in one dimension. And look at this. Here I have written the initial length as L1 and not just L. It doesn't really matter. Yeah, they are the same thing. I have written it as L1 just to ensure that you are aware that some books might use L1 as well. Yeah. Now, my question is, if the expansion in one dimension, or if the expansion in length is this formula, what about the expansion in area and volume? It is very simple as well. So, in terms of expansion in area, think of it. Here, the expansion is happening along two axes, in x axis and y axis, in this particular plate. So, what do you think is the formula? It's very simple. Yeah. Think of it. Change in area delta A equals, since the expansion is happening in two dimensions or two axes x and y, we write it as 2 times alpha. Initial area is area 1 times the change in temperature, and the unit is meter square. Is that okay? Yeah. Now, you know what? I want you to pause the video, take a sheet of paper, and try to write the expansion and volume equation. The only thing is, here the expansion is happening in three axes, x, y, and z. So look at the equation for change in length, change in area. So what do you think is going to be? Would you like to pause it and try? Okay. I hope that you have also written the units for this. Have you? Okay, if you have, let's see. This is the equation. It's that simple. 3 times alpha. Why 3? Because the expansion is happening in 3 axes or 3 dimensions. Alpha times v1. Change in length is L. Change in A, here it is A, so V is V times the change in temperature, and the unit is meter cube. Now, my dear people, we have looked at this as an engineering concept. Now, what we are going to do is we are going to solve a problem on thermal expansion. Yeah. So, what do we have here? A 2 meter copper rod. So 2 meters. So this is initial length L is heated from 20 degrees Celsius to 90 degrees Celsius. This is T1 initial temperature and T2 final temperature. Please make sure that all the units are in SI units. Yeah, if the 2 meter is given in centimeters or millimeters, please convert them into meters. Yeah, and make sure that both the temperatures are in degrees Celsius or in Fahrenheit or in Kelvin. Just make sure that both of them have the same unit. Is that okay? What else do we have here? The thermal coefficient of copper, okay, is 16 times 10 power minus 6. This is the alpha value, and they want us to calculate the change in length delta L. Why don't you pause the video and try to work it out on your own? Now, if you have worked it out, well done. Let me show you how it's done. All that I'm doing is I'm writing down the given. So we know the initial length, initial temperature, final temperature, and the thermal coefficient. What do we have to find? The change in length. What is the formula? Change in length formula is delta L equals alpha times initial length times change in temperature. Now let us substitute everything that we know. There you go. And use your scientific calculator. I know some of you use your phones, but try to use scientific calculators. It would be easier for you. So when you put this in, I get the answer of 2.24 millimeter. So what does it mean? When we heat this material, this 2 meter copper bar, it is going to expand by 2.24 millimeter. That is what it means. Now, I have a task for you all. Why don't you, okay, you formulate a question on change in area and change in volume? Can you write a question of your own? Let me tell you, to solve a problem, it's quite a simple thing, but to form a problem, yeah, it takes your intellectual ability to the next level. So why don't you form a problem um, based on measuring change in area and volume? Now the next one is, why should we learn what we are learning? So let me take you on a train journey on a hot, sweltering day of around 40 to 45 degrees Celsius. Yeah, it's a very pleasant train journey, and let's just go along the train, enjoying the views of the train. Whoa, my dear people, what do you think happened? Huh? Don't worry, there was no material damage and everyone was safe. So what had happened here, if you had noticed, was, let me show you, there you go. Over here the rails had expanded because of the heat and they have buckled. Do you see? why it is important for us to learn, measure thermal expansion. And as a solution, yeah, for the rails expanding, that is the reason why you see a gap between two rails. Have you seen this before? If you have seen this, it is to make sure that on hot summer days, when the temperature is high and the rails are expanding, they can expand into this gap so that it is. And also, if you see in some of the bridges, they have this so called expansion joints, where on hot days, when the bridge is expanding, it can expand into this gap so the bridge stays safe. I have given you a few more examples, but then I want you to think of a few examples of thermal expansion and come back to me. Is that okay? Huh? Even even if not for engineering application, whenever my grandmother asks me to open a lid for her, Venkat, can you please open the lid for me? It's really tight. All that I do is I pour warm water on the lid. So, what happens? The metal expands and it is easy for me to open it. My grandmother is so happy that I did engineering. Now, now, my dear people, if someone asks you, what is the height of Eiffel Tower? What is the question that you should ask them first? What is it? What exactly? What is the temperature on that particular day? Fantastic. Or if it is summer or winter, etc. Well done. Well done. If that is what you said or thought, fantastic. Fantastic. Huh? So we started with the Eiffel problem, and uh, now we have solved the Eiffel problem thanks to whatever we have learned in thermal expansion. Bravo! I'm really proud of you for having learned this, my dear people. Okay, next week, what I would like to do is for us to combine whatever we have learned in statics. Do you remember? We learned about stress, strain, Young's modulus, factor of safety, etc. So we are going to combine that with thermal expansion. Yeah, and we are going to look at the so called thermal stress. I'll just introduce you to the basics of it. You would really love it. Now, I've always told you, whatever we are doing in the session, yeah, in which we look at the theory, is just one part of your learning experience. I have designed a complete holistic learning experience for you, in which you will be using the theory in the lab to take some readings and to do some of the activities that I have designed for you in the lab. And then you are going to do some group based and independent learning. And based on the theory, the lab work, and your group learning, you are going to work on a mini interdisciplinary open ended project that I have devised for you all. It is just going to take 2 hours or so. You will be working with students from different disciplines and try to come up with an idea. Always remember, my dear people, engineering and physics is not just about knowing a bunch of equations. It's about what are we going to do with these equations? How are we going to apply, and how are we going to make a change, make a difference in the society and in our own practice? That is what it's all about. It's not just about knowing, it's also about doing. And this holistic learning experience I am devising for you is going to bridge the gap between knowing and doing, and it's going to give you a lot of creative approach to solving a problem. Okay, so what is that mini interdisciplinary project? Aha, you have to wait till you come over to the lab and I will explain it to you in detail. Is that okay? Huh? So, in summary, today, in the last few minutes, we looked at what is thermal expansion as an engineering concept. We looked at the area, volume, and linear expansion. We looked at some of the applications. We used mathematics as a tool. And finally, I introduced you to the mini project. My dear people, since this is a basic aspect, these are some of the books that you can refer, and also all the online materials that I have uploaded for you. Before I say goodbye to you, yeah, why don't you scan this QR code and do this mini activity? So when you scan this, it goes to a Padlet where you can write whatever you have learned in this session. The reason is this is going to create an ecology of learners. So you can read what other students and scholars have written, and you can learn from whatever they have written, and also you can contribute to their learning. This is fantastic. Yeah, you are going to be co-creator of knowledge, and that is fantastic. Yeah, my dear people, I'd like to say thank you to you. Have a wonderful time, and I'll see you all in the lab. Bravo. Bye.